Good afternoon and welcome to MAE 106. This is Discrete Mathematics with Probability. My name is Richard Kohar and this is Lecture 12. We'll be covering sets and we'll be covering in the textbook 3.1 and 3.3. Again, hopefully everyone can hear me okay. If so, just say so in the chat, thumbs up. Make sure that we have a very good video connection. Okay, excellent. So as a reminder, we have a test this Friday during lecture. Make sure that you keep an eye on the Moodle site where there'll be more details posted. And we'll also talk a little bit more about that in tomorrow's lecture. And this will be done over Zoom. So make sure you have something that has a webcam. Okay. If you have any issues with that, just make sure you send me an email. Okay, so this one we're going to be talking about is an introduction to sets. So underlying mathematics we study in algebra, geometry, and almost every other area of contemporary mathematics is this idea of a set. A flock of ducks, a troop of kangaroos, a wardrobe of clothes. These are all things that are examples of sets. So here's our definition of a set. It's a well-defined collection of objects. So well-defined, meaning that there's some sort of property or attribute that this collection or roundup of objects or things that they all share in common. Okay. And these objects that are in sets, in math we call them, these are called elements. So in this course, we'll have three ways of describing a set. So the first one that we could do is say with using a Venn diagram. Okay, so a Venn diagram is kind of our way or a graphical representation of a set, where we use a circle to represent a set and a dot to represent an element. So if I had, for example, Oh, and U is what we'll call the universal set, but we'll talk and define about that a little bit later. Okay. I know you might say, isn't the universal set a set, so shouldn't it be a circle? Yes. But let's just say that it's special, so we'll give it a different shape. And because I can't draw circles very well, I have a template. So we'll call this A. Now I should also say that with sets, and we usually denote them with capital letters. So these are things like, A, B, C, dot, dot, dot. And objects that are in the sets are called elements, and we denote these with lowercase letters. Okay, so I have drawn the set A here, and what am I going to put into it? Let's say 3 elements here. So sets are circles in a Venn diagram. Elements are dots. And so what you could say is that A is the set of the first 3 letters of the alphabet. Okay? So that's one way, a Venn diagram. Okay. Another common way of describing a set is using a roster notation. So same idea as like if we were at a ball game, the roster meaning a list of players. It's the same idea when we start to use this for set theory. So roster notation, we can write that using elements of a set by listing each element between curly brackets. So you can just think of that as listing all the elements. Okay, so if I wanted to do the same thing with this, with our Venn diagram, well, what I would do is I would use A, and I would say that this is equal to, here's my curly brackets, and I list off all the possible elements inside of it. So I have A, B, and C. Note that the order doesn't matter. But you only need to list them once. So in this case, I could have written it as CBA or BCA. I think that's, Okay, so those are all ways of writing it. And And we use a comma to separate each of the elements. Okay? So it's very similar to what we do in English when we're writing out a set, or sorry, a list of things. We put commas. The only thing that we do different is we add some brackets. Okay. We'll have to get to that question. Somebody has asked a question in the chat. That will be for later. We'll get to that soon. We'll be talking a little bit more about set operations. But that's a good question. Okay. The third way in this course is by using set builder notation. And so in this case, what we do is we give a rule that the element has to have. And so it's a rule or a property. All the elements have to. Okay. So there's a little bit more notation to introduce. So for instance, I need to introduce the idea of the special character here. So just a second. So let's say here I have x, and then here's this epsilon, Greek letter epsilon, and here is a. And what this says is an element of. So what this reads then is that x is an element of A. So that's just how we read that. And similarly, if I put a line through it, like that, this is not an element of. Okay. So if we were thinking back to our other running example where we had the Venn diagram and we had the first three lowercase letters, I wrote it out with roster notation. So here's ABC. Then using the set builder notation, what I can say is A, and so I use my curly brackets. I'm going to define a set. So I kind of write out my curly brackets. And what I would say is that X is in the universal set. So again, here it is. So we have the elements are in the universal set. So we're going to talk about A such that X is the first three letters. So notice that it's not necessarily that x is one of the first three elements, it's or the first three letters. X is simply a placeholder. We're just saying that here it's all elements in set U. This line here such that, and then here is kind of that property. Okay. So I've kind of danced around this for a little bit, and so I get to define it now. Here's the universal set. And what is it? It's the set that contains all the things that are of interest. So what does that mean? Because a universal set could be quite vague. For example, I could be talking about all types of grapes when I'm talking about wine. Right. And inside of that universal group, I could have like red wine or red grapes and white grapes. If we're talking about, say, card games with gambling or poker, bridge, blackjack. So, for instance, when we're talking about card games, we would be interested in the standard deck of cards. And probably if you haven't seen a deck of cards, there's 52 cards in there. There's 4 ranks and there's 4 suits and 13 ranks. Yeah, and it has like the heart, the spade, the club, and the diamond. And the ranks go ace, 2, 3, ... all the way up to 10, jack, queen, king. So there's the 10, and then the 11, 12, 13. So 52 cards. And we usually denote this universal set with a U. Okay. So we talk about universal set, so it's the set that has everything of interest to us. The opposite of that would be the empty set. the set that contains nothing. Okay, and we can denote this as a set of empty brackets, or you can also write it with kind of a circle with a line through it. This is also if you're listening or eavesdropping on mathematicians. Some people will also call this the null set. Okay. Just in case that I accidentally drop that, but drop the term. The empty set is again a set that has no elements. Okay. Sometimes we're required to find the number of elements in a set, and these types of problems are called counting problems. Which essentially boils down to how many elements are in a set. And this can be quite straightforward if we're working with something that's finite. It's a little bit more trickier when we start to talk about infinite sets. So finite and infinite. So here, let me just start off with saying that the number of elements in a set, we'll say A, is denoted by n, and we'll write of A. So if we go back to what we thought about for our first example here with the Venn diagram, the number of elements that are in this set here, A, is 3. So you could also say, let me just write this with a different color pen. The number of elements in set A is the number, or n, of A is equal to 3. So we'll use this notation to mean the number of elements in the set. So you can have finite. So here are examples of that. So I could say A is equal to 1, 2, 3, 4, ... Oh, no, I don't want to do the ... Sorry. We'll do 5. There. We'll do B. You can pick out like 2, 4, 6, 8. So what this does is it lists all the elements. When we get to the infinite, we're not able to list all the possible ways of doing it. So, for instance, we could do the set of odd numbers. And so that would be 1, 3, 5, 7, ... And this goes on to infinity. We could do the even numbers, 2, 4, 6, 8, 10. So in this case, the number A is 1, 2, 3, 4, 5. The number B here, 1, 2, 3, 4. Are infinite, meaning that it's infinity and it's also not a number. Okay. So the number of elements in a set is denoted by n of A. And this is also in math people is also known the cardinality of the set. So there's a lot of terms that we're kind of working through here. It's just kind of getting a grasp of all the definitions and terms and ways of writing what a set is. But it really just comes down to how are we defining a list or a collection of objects. So again, there's three ways of doing it. We can use a picture using a Venn diagram. We can write them all out like a roster for a sports team. We can also write it if there's too many for us to kind of write all out, like it takes us a long time, like there's 1,000 players or something like that. Well, then we can kind of write out a rule or a property that all these elements would have, and that would just kind of be our shorthand for expressing that set. We have the universal set, we have the empty set, and then we want to know how many elements are in that set, which leads to us for counting problems. So somebody has asked, okay, so here is the question somebody had asked. We had if A is equal to A, B, C, here's an empty, somebody has asked this. Well, the first thing that we notice is that I'm not sure if this is an issue with, it's not a question that I've asked. I don't know if this is a repetition, so I don't have to worry about this. Oh, the question is coming from the chat. The other thing is it depends on okay. What is the yes, okay. And there we go. The other question is, somebody is asking about this. I'm not sure about this empty set here. Could you count it as an element or not? So what I would say is my answer for this would be I would count it as it. And I would say that the n of A is equal to 4. So there's a repeated element. And again, we want, if we're using roster notation, note that the order doesn't matter, but we only list them once. Okay. Yeah. I think this is a good time for me to kind of bring up one of the examples that I had. Just a second. Okay, so before we go further, what I'll do is I'll define what a subset is. So a subset is where we have a set that's inside of another set. So I have, I'll switch colors. I'll call this A, and the other one I'll call, let's go with a bigger one, circle. There we go, B. would say that A is a subset of B. There are some people that will make a distinction of a proper subset. So a proper subset, just a second. They mean by a proper subset So again, I'll draw my Venn diagram here. I have my A, B, so what they would say is that A is, oh my gosh. We'll say that this is a proper subset of B. And when they say a proper subset, it means that at least one of the elements in B is not in A. So for instance, I could have A, I could have B, and here's C. So at least one element in B is not in A. So in this case, they don't care. You could have all the elements. In this case, when we write A as a subset of B, we have all the elements are in A, and there are also all the elements in B. So they don't really care in this case. But with a proper subset, there has to be at least one element in B that's not in A. In this case, it's C. So if I wrote this out, I have A and B. And for B, it'd be all the elements in A, and in the extra element there, C. And that kind of brings me up to equal sets. A set is equal if each set contains the same elements. And you would write it like A is equal to B. So in this case here, A is equal to B. But in this one right here, A is not equal to B because there's that one element, C, that's not in the A one right here. Okay. Why would B exist in the first example? Why would it? It's a set that, it'd be something where both of them have the same properties. I hope that answers it. Sometimes the sets that we come up with are equal. But that's what kind of this idea of that little line underneath it means. Yes, it's a possibility. It's not necessarily theoretical. It could crop up. I'm just trying to come up with an example on the spot. For example, here is quite a possibility. Are you ready for this? Let's say you have 3 friends. It'd be pretty. Hopefully they have something. Hopefully they have a nicer name. You have, I don't know. You're in the 1950s. Your 3 friends are Alice, Bob, and Charlie. And A would be the set of tea drinkers. And B, the set of coffee drinkers. And in fact, they're both tea and coffee drinkers. So there's kind of a silly explanation for why something could, all the elements in one set be in these another set. But someone asked, how would a test question look like regarding sets? Well, we haven't. Okay, so somebody's asking. Yes. Somebody asked me about what would the questions look like. Something would be like drawing a Venn diagram. Something would be like doing the roster notation for a set. Building a set. Or another thing could be writing. Yes. Let's do an example. Okay. Oops. Let's go on to 5. Okay, 5. Unfortunately, with the question that somebody's asking, we haven't gotten to that part yet with set operations. So just a moment. We're taking it really slow. Okay. And I have one more thing. We'll do the power set. And that is, we usually write it as P of A. And this is the set of all sets. The set of all subsets of A. Including the empty set and A itself. Okay. So that sounds kind of can kind of sound vague. So what I'm going to do is let's do an example. Where I will list out all the possible subsets of a set. So here's an example. Let's say, and we're going to keep it really simple. Let's say that we're going to go to Subway and we're going to order a sandwich. And we're going to say that we have toppings. And I'm going to pick, like, I know there's a lot of toppings that are available. But let's say that we'll say lettuce, tomato, and we'll go with spinach. Okay. And I know there's lots of sauces and there's lots of, but we're going to try to keep this simple. So the first thing the sandwich artists ask, let's say, do you want lettuce? Okay, and so you can go, I love spinach. You know, we can say no or yes. Okay, so over here, there's no lettuce. Okay, well, then that's an empty sandwich at the moment. Yes, I love lettuce. All right, so then it's an L. So then the sandwich artist asks, do you want tomato? I love real world examples, and probably because I'm hungry right now. And afterwards, I'll probably go to Subway. Okay, and with this one, again, if you said no for a tomato, then okay, it's a pretty boring sandwich. It's just going to be the bread or a flatbread or whatever that you pick. Anyways, okay, so with this one, yes. Okay, finally we have something interesting there. There's a T. Okay, so with this one, we said no to the tomato, but we're going to carry this forward from the lettuce, so it's just lettuce here. We're going to carry this forward. Here's an L lettuce, T. You mean lettuce? Am I spelling this wrong? Of course, probably. Yes. Thank you. Then we said the last question will be spinach. Hopefully I'm spelling spinach correctly. Unless it's spin-ak. Spinach, I don't know. That's spinach. And again, the sandwich artist would say, oh, okay, yeah, you want it? Yeah. So there's two options for this. Two options for this. Okay. So you go no, yes. Okay, I'm just writing X, check. So, no spinach, so there's nothing for the lettuce, the tomato, nothing. So there we go. Yes. Okay, so I have tomato and spinach. Oh no, I said no for the that one, so there's nothing for this. Okay. But so we had tomato and spinach here. No spinach, so it's just lettuce. Here is lettuce and spinach. And here is lettuce and tomato. Here is lettuce, tomato, and spinach. So again, right here is the empty set. Right here is the original set that we had here, A. So the set of the power set is the set of all the subsets of A, including the empty set and A itself. So the power set of A is, and then again I use some brackets again, even though, so I have the empty set, so there's a sandwich with a really boring sandwich. I have the sandwich with spinach. I have a sandwich with just tomato and spinach, lettuce and spinach, lettuce, tomato, and I'm gonna cheat and just write A. So then the question is what is the number of elements in the power set? Well, that's 1, 2, 3, 4, 5, 6, 7, 8. Okay. It also works out to 2 to the 3. And this is just something that we can kind of point out quickly. I will get to prove this later, but here's a theorem. The number of elements of a set, the number of subsets of a set n with, of a set with n elements is 2 to the n. So that means, going back with our original example that we were working with this subway, the number of elements was 3. So the subway example is n of the power set A is 2 to the 3, which was 8. So because we've generalized that, instead of me having to do, let's say I have B, and we had lettuce, tomato, spinach, and they had like hot peppers, and then they had I don't know, olives. Okay, how many sandwiches could you have from that? Which, again, a mathematician would be over here, be thinking like, look, that's an example of a counting problem. Well, the answer is the power set of that, which is 2 to the 1, 2, 3, 4, 5. So 2 times 2 times 2 times 2 times 2. So I think that should be, is that 32? Why were we able to do it so quickly? Well, we knew from this theorem. So that's how we're able to do something very quickly. Instead of doing a large kind of table like this, we're instantly able to count something very quickly and very sophisticatedly. So while it may sound kind of juvenile or like kindergarten, like how counting things, we're counting in a very sophisticated manner now. So that's just one example. Okay. Let's talk about set operations. That's 32 different that's 32 different combinations. Yes. Yes, that's correct. It's combinations because the order does not matter, unlike permutations. So you can kind of think of this as using old sets. To get new sets. Okay. So we're going to use the same idea. Oops. All right. And I will use I'll use a different size too. So U. So we can say A and we'll say B. And this is what we're going to look at the union. And that's where we'll have like A union B. And that represents all the elements that belong to A or B. So it's all the elements in A or B or both. And that's what we use. We use kind of this cup, or it kind of looks like a U, so that's for union. Let me use the set builder notation. So using set builder notation, I can say that it's all the elements in the universe such that the element is either in A, and there's the disjunction coming back from logic, or B. It's the or from logic. So we know from logic that or means that it either has to be an A or B or both. So what we usually do then is we fill in or shade what the area of interest would be. So I'll pick a different color. Doesn't have to matter. It doesn't matter. I'm just going to shade it in. So it's everything in A. Okay, so it's everything in A or everything in B. So everything in B. There. So I'll just kind of label that as A union B. So I'll just kind of say that's read as A union B. Okay. So I'll just draw this a little quicker. So there's my universal set. So here's in my example. So let's say that I have my two sets. There we go. Say A is the set of coffee drinkers. We'll say B is the set, these little what I'm trying to think what it is in Canadian English. These inverted commas or these little ticks mean that I'm just copying down from the previous one. So is the set of tea drinkers. So in this case, if I said I wanted A union B, well, it's all the set that's in A. So A, quotation marks, thank you. Yes. So there's all of the elements in A, and then I have all my elements in B. But remember, note that I do not copy out the same element twice. It's only once. So what does that mean? If I said the number here, how many elements are in the union? That's equal to 1, 2, 3, 4. So what would be, so A union B represents I was thinking tea or coffee drinkers. You could think that this is like hot beverages. drinkers, say from a particular cafe, from Brucey. So that's just the way that we can combine elements. We can, or sorry, combine sets. So I can take two sets that I already have, and I can combine them together with the union and create a new set. And that's the set A union B. Through 7. Let's do the intersection next. So you can kind of guess what we're going to do next is we had used the logical OR previously with the union. So we had the OR here. In this case, it's going to be switching now with the... So does the union act exactly the same as... Yes, it does. Yep. That's the logical OR. So that means that it's in A or B or both. Yes. Okay, so when we do the intersection, we'll do A intersect B. And so this is all the elements in A and B. So if I write this out as A intersect B, it's all the elements in the universe, in the universal set, such that the element is in A and is in B. Okay. So the Venn diagram for this so here's my universal set. A intersect B. Make sure that I label my sets A and here's B. So in this case, it has to be both in A and in B. So in this part right here, oops, magic of pencils. So in here, these are all the elements that are in A, but they're not in B. So this shaded section that I've just done here is not included. Similarly, all the elements in here are also not in A. That's kind of where we get the idea of intersection. They overlap, they intersect with one another. So visually it makes sense to call it an intersection. So it's just all the elements now here. So if I pick an element in here, that element is both in A and in B. So I'll just shade this all in. So then, when I come up with an example here, so this is kind of my example here. And I'll use that tea drinker and coffee drinker again. So let me just kind of, here's another set, here's another set. I had A, B, C, and over here is D. And again, same coffee drinkers. So A intersect B. We're just looking for those elements where it's both an A and B, and in this case, only C is. Which means that the number of elements in that intersection is 1. So again, if A was coffee drinkers, and B was tea, A intersect B represents coffee and tea drinkers. Okay. The next one that we have is the complement. And let's say we use this A prime. And that is all the elements that are not in A. So if I kind of write this out using my logical approach, using the roster notation, it's all the elements in the universe such that X is not an element of A. Okay. Draw this out. So there's our set A. So it's all the elements that are not in it. So it's everything outside of that set. So again, it's all the elements in the universe U that is not in A. Okay, and that's a complement. My coloring. Yep. So if I do my I have an example. If I have a universal set, and let's pick something, I don't know. I know this is a very trivial example, but again, here is my universal set. It's 1 through 9. I have A, which is 3, 4, 5, 6. Then the complement of this would be all the elements in the universal set that don't include A. So I would have 1, 2. I wouldn't have 3, 4, 5, 6. I would skip up to here, so 7, 8, 9. Okay. What's the next thing? Difference of two sets. So here's the difference. I'm not sure if this is as commonly seen in school, in high schools, but here's the difference of two sets. What we usually write is it's like B set minus A. So you can think of it as starting out with B, and then we take away all the elements of it that are in A. So it's all elements in B that are not in A. So again, we can think of it as all the elements in B such that they are not in A. So again, we can draw a little Venn diagram for this. We'll draw our two sets. So here's A and here's B. So it's all of the elements in B such that they're not in A. So this part right here is what we don't fill in, because that, although it's in B, is in A, and that's what we don't want. So you kind of get this crescent shape. So you can think about it as starting out with all of the B, and then you take away A from it. we should do the same thing. If I go over here, I'll just kind of, because of we're doing some sort of like removal or take away, the order matters in which you write it. So if you wrote A take away B, or A set minus B, so over here this means that's all the elements of A such that it's not in B. So same idea. So in this case, it would be all the elements in A, and we're going to take away the elements that are in B. So it just leaves us with the crescent shape, but with A on the A side. There. So let's do an example. I'll give you a Venn diagram for this. So I know that these might look really simple, like we're using like one or two elements in a set, but again, the sets can be quite large, complicated. Okay. So for this part, what I can do is I can do, say, I want to do A take away B. So in this case, I have all my elements in A, so it's 1, 2, 4. And I take away from 2, 3, 4, 5, and 6. Those are all the elements in B. So what am I left in with A? Well, I had 1, 2, 4, and the elements that are shared, or the elements that I'm going to take away, so B is going to come in and take from A, is the 2 and the 4. So what I'm left with is just 1, and that's for A take away, or A set minus B. Okay, same thing. I'll just copy this out. So in this case, the ones that are being shared, or the ones that A will take away, is the 2. So I can see that This will come in and take the 2. I also see that the 4 is going to be taken away. And the 1 isn't in B, so I don't have to worry about it. So what I'm left with is 3, 5, and 6. And we can see that visually right up here. So the 3, 5, and 6. So it's not too difficult, these concepts, because what we've kind of seen is previously from logic, it's just different labels for these now, these concepts. The other thing, we have a special case where if two sets have no intersection, we call that disjoint or mutually exclusive. Which can be a little bit confusing because when people say that they're dating and they're mutually exclusive, that's a good thing, and that they're together. But in math, we seem to take a more pessimistic approach. When we say that sets are mutually exclusive, it means that they are separated. So here's A, here's B, and that the intersection is empty. If they do not share any elements with each other. So let's say, for example, I have the set of odd numbers, 1, 3, 5, 7. These are infinite. It's an infinite set. These are the odd numbers. And over here I have the even numbers, 2, 4, 6, 8. Again, that's an infinite set. And this is even. They share no elements. Therefore, they're mutually exclusive. We can also think of, what else can we think of? Let's say that M is the set of planets in our solar system that have moons planets without moons and that these would be mutually exclusive, meaning that the set of planets with moons and the set of planets without moons is mutually exclusive. And if you wanted to be picky, I was quite specific. I said in our solar system. So U is the set of planets in our solar system okay. Oh, that happens. Oh, yes, thank you. It's a set of planets that, oh, yes. That moons, oh, yes, that would, that has a different interpretation in English, yes. You don't want a planet to moon. Yes. We need to be neighborly to our other planets. Should have some sort of good neighbor policy. Okay, so now that we've gotten some, we got some Venn diagrams. Let's play with the union, the intersection, and the complement. So let's say, for instance, I would have A union B, and I would want the complement of this. Okay, so with this, flipping back to our notes, we know that the union is everything that's in A and B. So every, see if we can pick something bigger. There we go. Okay, so with this, we know that everything is we have A union B is everything that's inside of A and in B, or in B. But with the complement, that means now that I need to have everything outside of that set. So again, this would be, I need the A union B, so it's everything, the shaded part right there. So I know it's all of this is here, but I need to exclude this. I want everything outside of that. So that's what it is. So it's, we are going to find that set and then apply the complement, taking everything outside of it. And that's what we do. So in this case, it's everything that is not in A or B, or both. So shade this in. And we're done. I can do A intersect B. So what that would mean is that it's everything that is not in both A and B. So with the intersection, we know, oh, maybe I should draw out the Venn diagram first and then we'll fill it in. Here's A and B. So we know that the intersection is right here, would be all that area in through there. And then when we take the complement, we want everything outside of that. So it's going to be everything outside of this shape right here. So if we fill this in, okay, so this one we'll do A prime intersect B. So if we kind of read that, it's everything outside of A that intersects with B. So if you're having a hard time visualizing that, I would say draw out the two steps. So here we go. Here's the first one. This one we would do like A prime. Over here we will do B, B, and then we'll do A prime intersect B. Okay. So in this case, what we have is A prime, so that's everything outside of A. I've killed a pen. Shoot. So again, everything outside of A. And now this one I would want everything outside of everything in B. So we need to find the two where they intersect. So in this case, I see, okay, for B, that intersects with this. I see everything in B. So what am I thinking? I'm thinking this. Here's everything in B. And then everything outside of A. So I would just draw it in different. So everything outside of A. Okay. So this is what I'm thinking. And the section where it overlaps is that crescent moon shape here with the B. So what do I fill in? It's just this part right here. And so there's the Venn diagram for A complement intersect B. So again, that's where is the overlap. Okay. Well, thank you everyone for tuning in today. I think we covered a lot of definitions for this. We covered quite a few terms. So again, practicing it will help as we go through this. 7, 6. Let me just quickly run through these sheets again. Must have misminted it. Again, remember that we have a test this Friday coming up, that a set was a well-defined collection of objects which contains elements. There was 3 ways to describe a set. We had a Venn diagram, we used roster notation, and we used set builder notation to describe a set. We had the universal set, which was the set of all the elements that were of interest to us. We had the empty set that has no elements that were inside of it. We talked about the idea of finite, which has a number assigned to it, and an infinite set that has no number that can be assigned to it. It's infinite, and infinity or infinite is not a number, it's a concept. We talked about a subset, which was a set inside of itself. So we had the subset and a proper subset. A proper subset has at least one element that's in one that's not in the other. Equal sets are where the same each set contains the same elements. We talked about power sets, which were a set that contains all the subsets of A, and we used the sandwich to kind of come up with all the possible ways of using 3 ingredients or 3 elements, and we found that that was 2 to the 3 or 8, so that makes it 2 to the n. We didn't have to draw out the entire sandwich tree for this one, where we had 5 ingredients. We found that there was 32 possible ways. Everything that we covered leading up to the test will be on the test will be on just logic, so it will not include the set theory. Then we have set operations. I hope that answers it. So I will just put that back. So that's just on logic. Okay, so it's just on logic. Then we had done the set operations. We had done union, which was all the elements in one set or the other set or both. We did the intersection, where it was an element that was in both sets. We did the complement, where it was all the elements that wasn't in the set. We did the set difference, where we had one set and we took away the elements that were from another set in it. We talked about mutually exclusive sets. These are sets that do not share elements with one another. And then we finished it with some examples of Venn diagrams. All right. Thank you, everyone, and I'll see you tomorrow. If you have any more questions, feel free to send me an email at my RMC account. Take care.